Okay, so in the last class, we discussed about the Newton's interpolation method, and we also discussed how to implement the method using Python here. And today we are going to discuss about the Lagrange interpolation method. And after that, we will see how to implement both of these methods in Python. Let me just first explain this part, and then at the end of the class we will see how to implement both of these methods, Newton's interpolation method and Lagrange's interpolation method, using Python. So what is Lagrange's interpolation method? And here it is also known as the Lagrange's interpolating polynomials. So what is this method? The first one is, as usual, the linear interpolation, as we have also discussed in the Newton's interpolation method. So first let's do the linear interpolation, and the approach is similar to Newton's divided difference method. Here we are assuming that the estimated function or the approximate function is a straight line. The actual function may be anything here between 2 points x0 and x1, and here again we are approximating that the function, the interpolating function, is a straight line, and the straight line can be represented by this form. And in the Newton's interpolation method, the form was a bit different, but that form is very similar to this one. So here, suppose the form of the straight line is like this. Now again we can find the constants a and b as usual, where this a and b are obviously two constants, and they can be determined as, when x equal to x0, f of x0 will be like this, ax0 plus b, and at x equal to x1, f of x1 will be ax1 plus b. Then if you subtract this equation 2 from equation 3, subtracting equation 2 from equation 3, you get f of x1 minus f of x0 as a into x1 minus x0. Then from that you get the value of a, right? So we got the value of first constant a. Then if you substitute the value of a, this value of a, in the equation 2, in this equation 2, then we can get the value of b. So this is the value of b, right? So just take this quantity to the right hand side with minus, and this will be the value of b. So now this equation 1 becomes, this equation 1, the function becomes this quantity here. And now you can further simplify it. There will be f of x0 here. There is a mistake. And here there will be f of x0 multiplied with this quantity. And as usual, see, you will get f of x as a form of, like this, where this is f of x0 and this is the f of x1 value. And here you see there are two functions that are acting as the coefficients of these f of x0 and f of x1 values, and these functions are known as the Lagrange's interpolating polynomials. As we have in the heading, this is Lagrange's interpolating polynomials. So these functions, this one and this one, are known as the Lagrange's interpolating polynomials. This is known as L0x and this is known as L1x. So how we determine which one is L0 and which one is L1? It is determined by the positions of x1 and x0 values in the function. And here we say that for the L0x, we see that it is x1 minus x and x1 minus x0. So this quantity here actually determines what is the value of index here. What is the index here for the L? So here it is L0 of x is x1 minus x and x1 minus x0. Similarly, what is L1x? L1x will be x0 minus x divided by x0 minus x1. So as here you see that this x1 and x0 actually represents what is the coefficient here of the Lagrange polynomial. These are known as the Lagrange polynomials. So this f of x, the function, the estimated function, can be represented by the addition of these two terms, and here these are the Lagrange polynomials. The functions L0 and L1x are called as the Lagrange interpolating functions or polynomials. They satisfy the condition L1x equal to Lix equal to I for x equal to xi, and it is 0 for x not equal to xi, right? So here you see that that when x equal to xi, that means when this x for this L0 case, L0x, when this x equal to x0, what will happen? Then it will, what will happen? Then this will become x1 minus x0 divided by x1 minus x0, and this is equal to 1, right? This they will cancel out and it will be 1. And when x not equal to xi, it is 0, right? When x is not equal to xi, when suppose this is suppose this x is now x1, right? Then what will happen? It will become x1 minus x1 divided by x1 minus x0. So here this x1 will give you 0 by x1 minus x0. So the value will be 0. So as you can see that these Lagrange polynomials have a property that the value of this polynomials is 1 when x equal to xi, and it is 0 when x is not equal to xi, right? When x equal to not equal to xi. So this is the linear interpolation formula. This function f of x equal to ax plus b with which we have started now can be written as this f of x function can be written as in this form, and these are the Lagrange polynomials. Similarly, we can do the quadratic interpolation. In the Newton's case also we did the quadratic and the linear interpolation, and then we did the polynomial or the general interpolation. Similarly, here we can do the quadratic interpolation, and for that we now need 3 quantities or 3 points, right? We need 3 data points for quadratic interpolation. There will be x0 y0, x1 y1 and x2 y2. So choose that the function is ax square plus bx plus c, right? This is a very general quadratic equation. And now using the conditions of the points at x0, x1 and x2, similar to the previous case, the value of the functions at different points x0, x1 and x2, you have to find the values of a, b and c. Similar to the previous case, when we found the values of a and b. The values of a and b. Similarly, you have to find in this case the values of a, b and c. And when you solve these 3 equations for the values of a and b and c, and when you simplify it further, the f of x function, this f of x function can be written as in this fashion. So this will be L0x f of x0, L1x f of x1, and then L2x f of x2, where L0x value is like this, and L1x value is like this, and L2x is value is this. These are the Lagrange polynomials for quadratic interpolation. Similar to the previous case when we found the values of L0 and L1. So here in this case the function will be like L0 f of x0, L1x f of x1, and there is an extra term for the quadratic interpolation, this L2x f of x2. Just give me a minute. Someone is at my door now. Okay, so this is the function for the quadratic interpolation formula, and these are the polynomials. Similarly, we can generalize this process or generalize this concept. So choose nth order polynomial passing through n plus 1 points. For this nth order polynomial interpolation, we need n plus 1 data points, and the function will be now like this, right? So it will be like a0, a0, a1x plus a2x square plus a3x cube, and so on up to an xn, right? So this is a polynomial of order n, and by using the conditions at different values of the points of the function, we get the values of these constants, and similarly you need to solve it further to get the Lagrange functions. I am not going to do them here because these are in book and you can see them, and these are not very important. You just need to remember the general formula. So this is the general formula, and this is the general Lagrange interpolating polynomial. So what are these symbols? You may not know. See, this is the summation symbol, and this is the product symbol. The product symbol means these terms will be multiplied with each other. Like in the summation symbol, the terms are summed together. In this product symbol, the terms are multiplied with each other up to a point. So here this is the general Lagrange polynomial, and this is the function, right? So this is the natural extension of the linear and the quadratic interpolation functions here, right? So here you see there the function is like L0, L1, then L2. Similarly here you have to add L0, L1, L2, L3 up to Ln with the function multiplied with to it. And similarly here you see that for this Lagrange polynomials, you see that there are extra terms. When we had the linear polynomial, there was only one term, and when we did the quadratic polynomial, quadratic interpolation, we had two terms, right? In each Lagrange polynomial, there were two terms. Similarly, if you do the nth order interpolation, there will be n terms multiplied to each other, right? So this is the Lagrange polynomial of the general order. And if you see how this polynomial works, let's see an example. Or let's find what is L2x. L2x and for the L2x value, the n is 2, right? The value of n varies from 0, 1 and 2. The value of n is 2. The value of n is 2. The value of n is 2, and it is right. So here in the product term, the j will go from 0 to 1 to 2, right? And so here, as you can see, that what is the formula? The formula is LIX is equal to product j runs from 0 to n. J is not equal to I, and it is x minus xj divided by xi minus of xj, right? So here the value of j will be like what? So you have to find, so let's find what is L2x. L2x value, right? What is L2x? L2x is this quantity here that we have derived in the quadratic polynomial. We have not derived it, I have just told you, but it is very easy to derive. It is very easy to derive, you can derive it yourself. Okay, so let's find what is L2x. Then L2x value will be, let's make the product terms, where it will be, the first term will be x minus x0 divided by x2, I is 2, then x2 minus x0, then the quantity will be x minus x1, because the value of j will go from 0 to 2, and xi value is 2, x2 minus x1, then it will be x minus of x2, then this value will be x2 minus of x value is x2. So here you see that this j equal to I value is not allowed, right? For this term here, j is becoming equal to I, means the value of j is 2 and the value of I is also 2. So this term is not allowed. Hence the value of L2x will be this, right? So the value of L2x is this, and as you can see that this exactly matches with the value of L2x here. So this verifies the formula here, right? Here you can verify this formula using different values of I and the different values of j, right? So this is all about the Lagrange interpolation, and here using that function, using this function, you can find the new data points. You have your old data points, and now using this function you can find what is the value of the new quantities, right? Using this function. Okay, let's now let's go back to our Newton's divided difference method, and let's see how to implement this in Python. So let me stop presenting now here, and now I will present. Here. Okay. So now let's understand the codes. So this is the first method, the Newton's interpolation method. Then here first we are importing NumPy. We need to use the arrays. So here the first thing we are doing is to import the NumPy module. We are importing NumPy as NP. Then we are taking an input from the user. Here input the number of data points you have, right? So input how many data points you have in your experiment. Then we are creating the x and y data values. Suppose this in our experiment, this x was current and this y was magnetic field, right? So this x was current and y is magnetic field. So here in this step we are creating a set of empty arrays, right? So this x is an empty array containing n number of data points, and this y is also an empty array, not exactly empty. The points are filled with zeros. So this np dot zeros means it is an array with all the elements having the value 0. So we are sort of creating empty arrays with the values 0. Then here in this step we are going to enter the data points. For I in range, all the number of data points you have, what are the values of xi and what is the value of yi? That means in our experiment, what are the values of current and what are the values of magnetic field? So enter the values of current and magnetic field. Here I have already entered the values. Here, as you can see, here I have already entered the values. So let's enter them again. So the number of data points we have is 6. Suppose we are taking 6 number of data points. Then the value of x0 is 0 and the value of y0 is 105. This data I am taking from the table given in your note from the previous lecture. And then the value of current is 0.04 and the magnetic field value is 174. Then the value is 0.14 and the magnetic field is 323. And then value is 0.30 and the magnetic value is magnetic field value 548 Gauss, right? Then 0.44 and the magnetic field is 753 and then 0.50 and the field value is 835. Okay, so you got 6 data points, and between these data points you need the new values. Suppose you need the value of the magnetic field at the current 0.2. So you have the data at 0.14 and you have the data at 0.3. Suppose you need the value of magnetic field at 0.20. How to get that? Using the interpolation method. So let's implement the Newton's method. To implement the method, you need to define the coefficient matrix as I have mentioned in the previous class. So let's make the coefficient matrix. What is the coefficient matrix? This one. This one was our coefficient matrix. In the first column, you have to first store the values of the y values, right? The f of x0, f of x1, f of x2, f of x3, f of x4. These are the magnetic field values or the y values, the y data. You have to store it in the first column of this coefficient matrix. So for this case, here we had only the 5 data points, but our case in the code we have 6 data points. So here the matrix will be, in our case here in the program, it will be a 5 cross 5 matrix, but here in the note it was a what? So here it will be a 6 cross 6 matrix, but here in our note it was a 5 cross 5 matrix. So there are 5 rows and there are 5 columns, but in our case here there will be 6 column and 6 rows because we have taken 6 data points. The number of data points are 6. So here we are first creating the empty matrix, the empty coefficient matrix, right? So np dot zeros will create an empty matrix filled with only zeros, and this will have n number of rows and n number of columns. The first n represents the number of rows and the second n here represents the number of columns. So n is 6, right? The length is 6. So that is why there will be 6 number of rows and 6 number of columns. Now what does this code represent? What does this line represent? This line represent the way we are entering the first column values. In the first column here as you can see with my cursor, that in this first column you have to store the y values here. You have to store the y values or the y data points or the magnetic field values. So here as you can see I am inputting that for I in range n, C of I0 is equal to yi. That means this 0 means this, what is this 0? 0 is the column. In the 0th column update all the row values, and this I goes from 0 to 6, right? Or 0 to 5, sorry. The I will go from 0 to 5. The I will go from 0 to 5. This for this 0th column, here for this 0th column update all the rows values, and in our case in the code it will go from 0 to 5, and that will have 6 data points. Here we had only 5 data points, and in the program we have 6 data points. I have taken an extra data point. So here in this column there will be 6 data points going from 0 to 5. Remember that. So now we have stored the y values in the first column, and then we have to update all the values in other cells, right? We have to get all this data now here in this column, in this second column, then the third column, then fourth, then fifth, then sixth. So for j in range 1 to n, and for I in range n minus j, you see we are updating the values of Cij. This Cij represents the elements of the coefficient matrix. So here this j is what? This j is the column index and this I is the row index. So j will go from 1 to n, means the columns will go from 1 to n, right? Here as you can see that the columns will go from 1 to n values. So here they will go from 0 to 5, right? So the column values will go from 1 to n, because we have already defined it for the zeroth row, sorry, zeroth column. For the zeroth column, the data points are already there. Then we have to update the values of the columns for 1 to n now. The zeroth column is already filled. So for 1 to nth column, for 1 to nth column, update the values of rows, and the row index I goes from n from 0 to n minus j. Why this 0 to n minus j? Because as you can see here, the row values in a column are not completely filled. They are filled in this way. So to satisfy this condition, they are filled up to the diagonal only. So up to diagonal only the row values will be fixed, and the elements or the cells below the diagonal will be empty. So here, as you can see that the row index will go from 0 to n minus j. Suppose we are at the first column, means j equal to 1, then this row index will run from 0 to n minus j. That means 0 to 6 minus 1. That means it will run from 0 to n minus 6 minus 1 means 5. Then it will run from 0 to 4, right? So here it will run from 0 to 4, as you can see here, right? So the column, the row I will run from 0 to 4, because there is an extra cell here for our case, and then that extra cell will be absent, and the row index will run from 0 to 4 in this case. And similarly, all the other cells will be filled. And what is this value? This value is telling you that they are this quantity here, this x1 x0 is the difference of f of x1 f of x0 f of x1 minus f of x0, and divided by x1 minus x0. Similarly, all the row values, all the elements are calculated like this. So if you put the values of I and j here, you will understand what is happening here. So just after finding all the elements of the coefficient matrix, it will return the coefficient matrix. And so as you have also created the coefficient matrix, then you have to define the interpolation function. Then you have to calculate the polynomial, right? Then you have to calculate polynomial. I left the meeting. So how to create the polynomial now? So insert the coefficients of the Newton's formula, means as you have now have the polynomials, then you have to as you have the coefficients, now you have to find the polynomial, the Newton's function. What is the Newton's function? This one. Yes. Yeah. Let me go back. So for this nth order interpolation, we are doing the nth order interpolation. You have calculated all the coefficients you have calculated. Then you have to find the the polynomial, this function you have to find the f of x function, and to find that we are defining this interpolation function, interpolate function. So define this interpolate function, and the inputs are, the first input is the coefficient matrix. You have to input the coefficient matrix to get the coefficients, then the x value, the old x value or the current values, and the x new value, at which data point you need the new value, right? For our case, we wanted to find what is the magnetic field at the current 0.2 ampere. So let's define the first term as coefficient equal to f of 0, 0. Then for j in the range 1 to n, and t is the coefficient. So what is this t? T is the these things. T is yes. So these are the actually the elements in the first row are the actual coefficients. This is the value of C0, and this is the value of C1, this is the value of C2, this is the value of C3, this is the value of C4, and there will be a value of C5. So the elements in the first row, are the actual coefficients. So these are the coefficients, or this t is actually the coefficients, and they are running from 0 to j, means in the first row these are all the coefficients you are inputting. And then for I in range, this t equals to t into x new minus xi, right? So here, as you can see, that how these coefficients are written. These coefficients are written like this. Like this, the C0, then C1 is multiplied with x into x minus x0, then C2 is multiplied with x minus x0 into x minus x1. So here you have all the C0, C1, C2 and C3 values in the t. Then you have to multiply the t with these quantities, x minus x0 into x minus x1, then C3 with all these three quantities, right? You have to multiply them. So here we are multiplying them again and again in the for loop, x new minus xi, and then we are adding all them together at the end, and we are returning the function. This function we are returning. This function f of x we are returning. So just put the values of I and j, take an example, and then you will realize what is happening here. So here you get the coefficient matrix, and then you find the interpolating polynomial or interpolating function. You get everything. Then let's take the actual values. So this a is the coefficient xy. So here we have the xy values, xy data points you have. Then now put a equal to xy coefficient. So here we are actually calculating the coefficient matrix. So if I now print this a, you see that this is actually the coefficient matrix. This has 6 rows and 6 columns. This is actually the coefficient matrix for the data points x and y, means the data for current and the magnetic field. Then you get for x new, that means x new is 0.20. So we wanted to find what is the magnetic field at the current 0.2. Then what will be y new? Y new will be the result of this function. So it is the result of the function interpolate, and the answer will be 406,417 and the numbers beyond that. So the answer will be close to 406 Gauss, right? So as you can see that here from the data, that beyond between 0.14 and 0.30, this 0.20 value lies, and the magnetic field should be between 323 to 548, and we are getting the value of the magnetic field as 406. So from the interpolation we got the value of magnetic field at 0.2 as 406 Gauss. And you can also plot your data, this XY data, using matplotlib. And here if I plot them, as you can see from this is the real function, this is the actual function. There is nothing interpolating here. In the actual function, you can see that at the point of 0.2 ampere, you see that it is actually correct. It is actually close to 406 Gauss, right? So the value of magnetic field at 0.2 ampere will be equal to or close to 406 Gauss. So that is how you get a new data point using Newton's interpolation method. Similarly, here you can do the Lagrange interpolation method. The first step is similar. The first step is same. Take the inputs of data points. Suppose we are again choosing 6 data points, and let's again find what is the value of magnetic field at the current 0.2, and this is the Lagrange interpolating function. Let's find this function. So this is for general case when there are 6 data points. So here we are taking this x and y data points as input, and xp, this is the new data point as the input in this function. N is length of x, or the value of n will be 6, because there are 6 data points in the length of x. Suppose s is 0, s is the summation. What is s? Here, yes, not here, yes. So we have to find these two values. First we have to find what are these quantities, what are the Lagrange polynomials. Then we have to add them together, multiplied with the function values, or the y values, or the y data points, or the magnetic field values, right? So we have to find this first, find the Lagrange polynomials, and then sum them together to find the function f of x, or the interpolating function. So if we are first, let's the sum equal to 0. The sum, all these sum are equal to, first let's them as 0. This sum as 0. Let it be as 0. Then for I in range n, and L is equal to 1. That means let that this L is 1. Initially the value of this Lagrange polynomial is 1. Then as we go further, as we do the product and as we do the sum, we will update the values of s and n. We are updating the values of s and n. So L is 1 for, and then for j in range n, so I will go, the sum will go from 0 to n, or 0 to 6, and then 0 to 5. As n is 6, the range will go from 0 to 5, and j will also go from 0 to 5. If I is not equal to j, why I is not equal to j? Because we are following this rule here. This constraint is that the I should not be equal to j. When I is not equal to j, we are doing the product. L equal to L into xp minus xj divided by xi minus xj. What is this? This is this quantity here, this quantity. So we are doing the product subsequently. When j is equal to 0, j is equal to 1, j is equal to 2, like that we are doing the product of this quantity. Then do the product and add them together with this L multiplied with the y data points, right? This L, the Lagrange polynomial, is multiplied with the y data point f of xi, right? So here you see we lastly find this, the sum, the value of sum, and it will return the value of the summation. So again, when the new data point is 0.2 and we want to find y new, and y new will be returned by the Lagrange interpolating function. This function will return the sum, and it is nothing but the new data point at a given new x value, new current value. So this will return y new, and if you print y new, it will again return this 406 value of the magnetic field. So again we get that at the current 0.2 we get the magnetic field as 406 Gauss. So the Newton's method and this Lagrange's method are actually giving you the same result. So for this case, you see the Newton's divided difference method and the Lagrange's functions are actually giving you the exactly same result. So they are very accurate and they are doing their job very well, right? So this is how you do the interpolation. This is Newton's method and this is Lagrange's method. Similarly, there is another concept known as extrapolation. What is extrapolation? This is interpolation. Then there is something called as extrapolation. Extrapolation is a process in which you have to find a new data point outside the range of given data points. Here what we are doing in this interpolation, we have a range of data point and we are finding the new values inside this range. But how to find new data points outside this range? That method is called as extrapolation. And if you want to read about it, you can read from the book I have suggested, that is available in the classroom, the first book. There you can learn about extrapolation. That is also very important. Extrapolation is more important than this interpolation method. And that is easy, not very difficult. You can read about it. But usually in our BSc and MSc classes, we do the interpolation. The extrapolation is not very needed, but it may needed in the research field if you are doing any kind of research. Okay, so that's it for today. Let's meet tomorrow, and tomorrow we will discuss about the system of linear equations, and after that the curve fitting methods. So that's it for today. Bye bye, goodbye.